All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Make sure we set things up here. What have we been doing? We've been talking about sets, but we got to a point where we wanted to do some examples. So we probably should jump into that right away.
Recording in progress.
Okay, make sure I can see the screen and the chat and everything. Christine looking a little extra frazzled today. It's okay. I get it. I get it. I do. I really do. I understand. Sometimes students don't think teachers understand, but we understand, really. You know, if I'm really going to be direct about it, you guys who don't understand. You know what I mean? One of the students often have these misconceptions. They think, you know, oh, it's easy for you to say because you're a teacher. You've probably always been good at math and blah, 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 which is, it's not true. Like a lot of teachers used to suck. I used to suck at a lot of things too. But another thing that I find strange that students often think is like, the professor doesn't really understand, you know? And it's like, one of the reasons I'm the teacher and you're the student is because I've been a student longer than you have. Like that's why I'm here, right? So I understand what being a student is more than you do. So it's always strange to me where students say, oh, you know, he doesn't understand, you know? Like, no, you don't understand. I get it, I do. Okay, so it's not a problem that, you know, you're tired or you're just like, oh man, I just want to be done with this. Like, I get it. But we are here. Let's make the best of our time. We cannot get this time back. So let's actually just do some of this. I don't know if a quick recap is necessary, but maybe I will do one just very quickly. Come back up maybe a couple of slides. So we started talking about sets. These were unordered collections of objects in which repeats are ignored. The notation is blah, where we can list what's called the elements or members of the sets. We can use this symbol here, which is like a little E thingy, to say that something is a member of a set. Two sets are equal if they have precisely the same members. You don't have to list the members in the same order, and you can repeat. In the event that we don't want repeats, that we want to count repeats, or we want order, we can use what's called a tuple. This is like an ordered collection where repeats are counted, and there are contexts in which we want to do that. We talked about finite sets and infinite sets. Finite set just means you can say it has some whole number, some non-negative whole number amount of elements, like it has 0 elements, or 1 element, or 2 elements, or 3 elements. The moment you can't actually say that, it's an infinite set. We also talked about the size of the set, that's cardinality. The empty set is the set with no elements in it. The empty set, we also spoke about subsets, where one, it's just like a sub collection of a previous set that you took. So it's A is a subset of B. If everything that's in A is also in B, that means that A was created from the things in B, right? And the empty set is a subset of every set. Every set is a subset of itself, and two sets being equal means they're subsets of each other. We did a few examples of that. We spoke about power sets, which is just a set of all subsets, very important thing in several contexts. And we know that the size of the power set is 2 to the n, which we looked at the argument for that. It was really something called the multiplication rule, which we'll be getting into next week. Not sure if we'll get to that on Tuesday. We might get to that at the end of Tuesday's lecture, but if not, somewhere around the beginning of Wednesday's lecture. Right, moving on. We've talked about sets being numerically equivalent. This just means they have the same number of elements. Sometimes we don't care about the sets being identical all the time, but we just care that they have the same number of things in them. We also spoke about common number sets, like the natural numbers, the integers, the rational numbers, the real numbers, the complex numbers, and some surprising equivalencies. These guys are all infinite sets, but it turns out that some infinities are bigger than other infinities, and mind-bogglingly bigger. Like an ocean compared to a drop of water is still not giving you the picture of how much bigger one of these sets is than the other one, even though they're both infinite in size. We also spoke about the universal set. We always consider that there is some universe in which we're working. Our sets don't just come out of thin air. There's no spontaneous creation of sets. There's a universe of stuff that existed in the background, and we use this universe of things to create whatever sets we're talking about. This is called a universal set. The complement is everything that's in the universe that's not currently in the set that we are considering. So if we have a set A, everything that's not in A, but of course exists in the universe, we call that that set of things a complement. I did some examples of that. We spoke about Venn diagrams. This is a way to visualize sets. It's a box with some circles in it. The circles represent the sets. Usually we label it by cardinality. So we talk about the number of things in each region in this set. And the box itself represents the universe. The circles in the box represents the sets. We also started talking about operations on sets, kind of like how we can do mathematics with them. There's no real addition and subtraction and multiplication, technically speaking, with sets. There's a kind of set product, but I might tell you about that, called Cartesian products of sets. But for now, the closest thing that we have to addition, quote unquote, is the union. This is when I take two sets of things and I combine them into one big set. Of course, I ignore repeats when I do this, but it's the set of all things that are in A or B or both. So with our notation, we can write this to say X is in A, or X is in B, or X is in both, right? Where this guy was defined down here. So we have that. And here we have what's called the intersection. So this is just finding all the elements that are in common to both sets. So this means that X is in A. This means that X is in A, and at the same time, X is in B. Set of all such things, we call it the intersection of the two sets. We read this as A intersect B. I think I didn't put that last time. Red. We say A intersects B for saying that in words. We spoke about the set minus, which is a kind of subtraction, but not really, because you can't really get negative sets or anything like that. But it's like when you start with a set and you take away all the things out of that set that is in some other set, you call it the set minus of one set versus the other. So the A minus B really means is you take all the guys in A, but they're not in B at the same time, right? So you just look at the guys in A, throw out anyone who's also in B, and that is your set minus. We can visualize these with Venn diagrams where we can shade the region that we're talking about. So the union is just like shading those two circles. And of course, a quick pro tip, you always draw your Venn diagrams to have the most overlaps as possible, because you really don't know where everyone's going to be. Whereas if you drew circles separately, then if there was anyone in common between both sets, now you can't actually represent that. You only kind of separate things if you know for sure, like it's a part of the problem that we know that these two things have nothing in common. But in general, you draw things with overlap, and it's fine. Even if they don't have anything in common, you would usually put just a 0 in the overlap. So you know, oh, there's actually no one here. I thought there might have been, but there's actually no one. This is what the intersection looks like. It's the guy that's in both. Here's the set minus A minus B. You'll notice that it is the things that are in A, but not in B at the same time. B minus A, the things that are in B, but not in A at the same time. Here's A and its complement. Pretty much everything in the universe that is not in A is called a complement. And then finally, we got to some examples where we can kind of play around with some of these definitions. And I actually threw in a few more examples also. So let's get to those. So we're going to do these examples. And then there are some word problems here that we can solve via Venn diagrams. which is also an important problem type for this course. So this is what we're going to jump into now. So the rest of this class is pretty much going to be me solving these examples and making sure that we're all on the same page with this stuff. Okay, so use Venn diagrams to conjecture the connection between these two sets. As I mentioned, pictures are not proofs. You can't really prove anything with a picture, but you can kind of illustrate something, get an idea of what the truth might be from the picture, and hopefully that's going to be useful here. So let's look at A. Someone's trying to get in here. Let them in. And here we have A complement union B complement. Okay, so let's actually draw Venn diagrams for both of these guys. So there are two sets we care about, A and B. I draw them with overlaps because I don't know if they're going to overlap really, but I want to account for that if they do. Okay. What would A intersect B complement look like?
You shade everything in but the intersection?
Everything but the intersection. So the intersection is here, but we don't want that. We want literally everything else, right? So that would mean that we're shading everything here. Literally everything but the intersection. Okay, now let's see. And that's pretty much it. If we go to the other side, A complement union B complement. What does this mean? It means we shade A complement and we shade B complement, and we take the guys that are common to both. So A complement would be everyone that is outside of A. So everything that is outside the A circle. So I'm doing that for A complement. And let's do, let's say, red for B complement. Now I want to shade everything outside of B. So I'm going to shade everything outside the B circle. Right? So the union means take any part that is shaded. You can kind of think of the intersection as being, you have to take the part where all different shadings overlap. That's one way you can think about it. But the union is indiscriminatory. If it's shaded, it's in the union, right? So now, what would your conjecture be about these two? How does one relate to the other? So on the left, the only thing that is unshaded is the intersection. What about on the right?
The intersection?
The only thing unshaded is the intersection, right? So in both pictures, the only thing that's unshaded is the intersection. What does that suggest?
They're equivalent?
They're equal. Equivalent means something else. I guess you could also say equivalent here technically, but yes, it suggests that they're equal. To take the complement of an intersection is exactly the same as taking the union of the complements. So that's what my guess would be. It turns out that that is true, but the picture does suggest that as well. What if I were to take the union of the complement of a union? So the union is everything that's shaded in either circle, but I want the complement of that. So I'm going to shade out what's outside of either circle.
What's the difference between equal and equivalent?
Equivalent means they have the same number of elements. Equal means they have the same elements exactly, right? So if I have the set A is A, B, C, and the set B is 1, 2, 3, they are equivalent because they both have 3 elements, but they're not equal because they don't have the same elements. One has letters, one has numbers. On this side, I wanted to use A complement intersect B complement. So let's talk about A complement. Let's shade that first. A complement is everything outside of A. And B complement is everything outside of B. Now, for the intersection, remember, intersection means everyone has to be satisfied at the same time. You have to be common to all sets. So intersection means intersection needs region where all shadings overlap, not just any shading. So in other words, so here, the intersection is going to be the part that's shaded like it has blue and it has red. Now, if you look at which part of this picture has both shadings, you'll notice that it is going to be the part that is outside both circles, just as in the picture on the left. So here, if I look at A complement intersect B complement, the real picture that I want to really take into account is the fact that this out here, you'd essentially ignore any part that only has one kind of shading. For intersection, ignore any region that does not have all kinds of shading. So we ignore the part with only blue or only red. You'll notice that inside the A circle, there was only red, while inside the B circle, there was only blue. We ignore those parts for the intersection. And so what we get so I would say from here, our conjecture is again, and a conjecture is just, it's a fancy word for guess. Conjecture means guess, right? It's the word conjecture is the mathematical equivalent of the word in science that's called hypothesis, right? So scientists have hypotheses, mathematicians have conjectures. So it's really just an educated guess. And the educated guess would be, if I take the union of the complement of a union, it's the same as the intersection of the complements. So it's like I can distribute the complements across all sets and then change the union into an intersection. It turns out both of the above are in fact true. They form a theorem, comprise a theorem called, does anyone know what these are called? Is there anyone who did set theory and know what these two things are called? Called De Morgan's laws. I don't know if anyone's ever heard that name before. So this says for any sets A, B, we have one, the complement of the intersection is the union of the complements. And the complement of the union is the intersection of the complements. Turns out this is true, and we can use this at any time. It's always going to be true for any sets. It's called De Morgan's laws. Very important, very common laws, and they allow us to prove a lot of things and figure out a lot of things. So that would be nice. So that's how you can kind of judge things by Venn diagrams. But again, diagrams only are kind of suggestions. You can't really use them as absolute proof for anything. However, in this class, I'm not going to ask you to prove anything technically. So being able to illustrate an idea is perfectly fine. Let's get a little bit more computational here with this one. Computational, because we're going to be, maybe analytical would be the right word. Because now we have very specific sets in mind. So my union is the natural numbers, and don't forget what this guy means. It means all counting numbers from 0 or bigger. And as I mentioned, not all sources include 0 in the definition of the natural numbers. So you have to be careful when you're reading the source. It'll usually tell you in the glossary, or it'll make you know some other way what it thinks the natural numbers are. Some people start from 1, some people start from 0. For various reasons. It's more useful to have 0 in there, but the real mathematical purists are probably like, oh, we start from 1. 0 wasn't invented till like, yeah, the story of 0. So it's another one of those mathematical oddities. You would think that 0 always existed as long as we've had number systems, but that's not true. It took a while for us to figure out, you know what, we should probably have a number for nothing. Like, why do we need anything if it's not even there? Like, you know, philosophical questions, like, you know. And then someone's like, what about negative numbers? Dude, I think there's a number like the square root of 2. What? That doesn't even make any sense. You mean it's not a fraction? What fraction is that? It's like a half, or it's like a 3/4? No, man, I don't think you can write it as a fraction. Ah! Yeah. Pythagoras, one of Pythagoras' students said that legend has it he literally like drowned him because of the blasphemy.
You seem a little frazzled today.
I do? Yeah. Yeah. She's just messing with me because I picked on her and kind of. Okay, let's go. I don't seem frazzled. I seem delirious would probably be the word. You know when you're so tired that you go to the other side, like you go to the negative numbers, and you're like, oh, this guy's about to knock out. It's like, okay, let's do it. Let's get into it. All right, so that's U, that's our A, that's our blah, blah, blah. Okay, let's, do that over here. So how about A intersects B? What is it? A is it's the set containing 3, right? So the intersection is also a set, right? So that's what's in both A and B at the same time. What's in A intersects C? A intersects C, what's in it?
Is it the empty set?
It's the empty set. There is no one in common. What? There was no 1 in common there. Intersect E. So E is the set of all positive even numbers. A intersect E, what is that?
Two.
The set containing 2. So 2 is an element. The intersection is a set. Move all these all at once. It's actually inefficient to move them one at a time because multitasking does not work. Pro tip here, guys, like you do one thing at a time. Yeah. Okay. Okay, what are we? A intersect O. What is that? A intersect O.
The set containing 1 and 3.
The set containing 1 and 3. Set containing 1 and 3. Yep. E intersect O.
The empty set.
The empty set. They have no elements in common. A minus B. What is A minus B?
Set containing 1 and 2.
Yep. So remember what A minus B means. It's like you start with A. Then throw away anything that is also in B. So that's what it means, set minus. Throw away anything also in B. So A minus B would be 1 and 2. C minus A. What is C minus A?
Set containing 4 and 5.
Yeah, it's set containing 4 and 5. In fact, it's just C, right? A and C had no one in common, so you couldn't throw away anything. So C minus A is actually just C. It's almost like you didn't take away anything. N, the natural numbers minus E.
Would it be the set containing 0 and O?
Yes, so this would be 0 and then 1, 3, 5, 7, da, da, da. Yep, you could also think of this as O union the 0 set, the set containing 0. E minus the natural numbers. E minus the natural numbers. What is that?
Empty set.
Empty set. Right? Because you start with E, and then you throw away anything that's also in the N. But literally everything that's in E is also in the N. In fact, E is a subset of N. So if I throw away everything that's also in N, I'm literally throwing away everything. So that's the empty set. Okay. So, I mean, hopefully that is making it conceptually a little more clear on what these definitions actually mean. What does it mean to subtract one set from another? It's not the same thing like you would think in numbers. It's just like you start with the first set and then you throw away anything that's also in the second set, right? And this leaves you with another set. Okay, so here, let's find these guys. Okay, A intersects B, A union B, A minus B, A union B, complement, A intersect B, complement, A complement. Okay, so here is our sets. Our universe is all the positive integers from 1 to 10. A is 1, 3, 5, 7, 9. So it looks like all the odd integers between 1 and 10. And B is 2, 4, 6, 8, 10, all the even integers between 1 and 10. What is A intersect B?
Empty.
The empty set. What is A union B?
One to 10. Set.
It's 1 to 10. In fact, it's everything in the universe. What is A minus B?
Just A.
It's just A. A complement?
B.
It's actually B, right? So it's everything that's in the universe, not that. It's everything that's in the universe, but it's not in A at the same time. You'll notice that that's just the elements in B. So I go into U, and then I ignore everything that's in A, and that's what's in A complement. What is an A intersect B complement?
About 11, 12, 13, 14 for D, like the other numbers in the universe that are above it, they wouldn't be counted as.
No. So as far as you're concerned, when I say this is the universe now. Like you pretend that there are no other numbers.
Okay.
Right.
Right.
So you literally live in a context where you ignore everything out of existence except here. Right. So yeah, the U represents all things in existence. So as far as you're concerned, 11 doesn't exist. Reminds me of this joke that someone said about the 9/11 deniers. The 9 people who didn't believe that the number 11 existed. Okay, never mind. Okay, so now A intersects B, you want the complement of that.
Would that be a set containing elements 1 through 10?
It would be the set containing elements 1 through 10. Right? That brings to light a very important thing that I'm going to mention here. I'm going to mention a little bit later on. But another way to see this, if you don't, is another way to see this. I mean, if you saw it right away, then great. But if not, notice that above, by De Morgan's laws, we know that this was the complement union B complement. Now, if I take A complement, that was 2, 4, 6, 8, 10. If I took the union, that was B complement, which is 1, 3, 5, 7, 9. So this is the A complement was actually B, and the B complement was actually A. If I take the union of A and B, we already found that to be the entire universe, right? So you can actually know that that's the entire universe as well. And yeah, so A union B complement. What is A union B complement? So A union B we know is the universe. What is the complement of the universe?
Empty set.
It's the empty set. So this is U complement, which is in fact the empty set. So the above leads to some important facts. This is actually true in general. The complement of the universe is the empty set. That's just something you can know now, as well as the complement of the empty set is the universe. All right. So remember, complement just means everything that's in the universe that is not in the set that you're looking at. So if I take the universe and I want things that are in the universe that are not in the universe, well, what? Like there's no such thing, right? So it's the empty set. Versus if I take everything in the universe that is not in the empty set, well, that's just everything in the universe because the empty set is empty. Like literally everything in the universe is outside the empty set, right? And so you can get that. You can prove that using De Morgan's laws. You can prove that in a variety of ways. It also just, if you think about it a little bit, it also makes sense intuitively, but that these are also some facts about sets that we can take for granted. So like that and De Morgan's laws, we can take for granted at this point. So, I mean, hopefully going through that, it kind of makes the definitions I've been talking about more clear, both in terms of diagrams and in terms of specific sets. Hopefully that helps. Now, let's actually move on to some Venn diagram section. How much time do I have left? Okay. So before starting these, I guess I will tell you best practices when finding Venn diagrams. We will want to be able to use Venn diagrams to solve word problems. About sets. Generally, the following approach is useful. So let's talk about the method for solving Venn diagram word problems. So one is to name sets set up sets to measure groups. You want to say something, Alex, or did you unmute by accident?
I unmuted by accident, sorry.
Okay, all right. To measure groups you care about. Right, so it's kind of like defining your variables. Just kind of have some shorthand notation for what you want to do. Now you're going to draw a Venn diagram. With all sets in part 1 accounted for. I will, of course, remind you at this point, remember, maximum effort. Maximum overlap should be drawn, unless you have a very good reason not to. In one sense also, it's actually like, you can think of it as never being incorrect to draw maximum overlaps, but you can be incorrect if you don't. So you have to be very careful. It is never incorrect to draw maximum overlaps. Worst case, you will find 0 elements in some overlap. So if you don't want to actually think about it, like you don't want to have to worry, should I draw this as overlap or not? Just draw it with an overlap. Like it's better that you have an extra overlap than you not have an overlap when you need one. So you would first define the sets, define your variables, then you're going to draw the Venn diagram, which means you draw a box, you draw a bunch of circles in it that represent each set, you overlap as much as possible. So if you have 3 circles, you need to have all 3 overlapping and any 2 pairs overlapping at the same time, right? Unless we are specifically told that one circle doesn't overlap with another one, and then you can adjust for that. So you're going to draw that Venn diagram. Then you're going to start to fill out the cardinalities in the Venn diagram. And tips here for doing this, because there is like a right and a wrong way to do it. These regions should be filled out first. Like if you mess up the order, you can get in trouble. 1, region where all sets intersect. So if you're given information in the problem that, you know what, every single person in the universe has this property, or they tell you that, oh, here's a group of people where they all overlap, you want to fill in that number first. Another region that you want to fill out first is regions designated as only. So a problem might say, there are only 5 people who are in this group and not in this other group. Then you can fill in that region, right? We'll see examples. The thing is, you have to be very careful with reading these problems. And you have to be careful because the mathematical language is going to be precise in a way where your everyday human language would not be. So just because someone tells you that something is the case, it does not mean that's only the case, right? Which a lot of times in everyday language, when people say, oh, this is the case, they're really saying, this is the only way it's going to happen, right? You know, so it's in math, that's not what it means. So in math, they'll specifically tell you this is only the case, right? And then you can say, okay, all right, I know that part. And another part is regions that, or I guess it should be region that is outside all sets. And of course, this is all, you know, provided this info is given. Step 4 would be, well, use basic arithmetic to figure out the number of elements in all other regions. And 5, answer the required questions. So steps 1 through 4 is just you setting yourself up so you can answer the required questions. So that's like a 5-step program to solving Venn diagrams. You first want to set up your sets, name your sets, draw a Venn diagram, maximum overlap, fill in the numbers in the diagram, pretty much in this order. You want to fill these in first. So you definitely want to fill in a region where 3 sets intersect before you fill in a region where only 2 sets intersect. You want to kind of fill in towards the most overlapping first, right? So I guess I guess that could kind of be a step 4. Fill out most overlapping regions first. Right, so you want to fill out the section where 3 things overlap before you fill out the sections where all 2 things overlap, before you fill out the sections where only 1 thing overlaps, etc. Unless you're specifically told only in that situation, then you can fill out that first as well. Let's do one of these, and then I'll leave the rest for you guys to do. We'll finish that up on Tuesday. Okay, suppose you have 100 people in a school. In the school, 50 students remember all the math they've ever done, right? So you poll all the students. You remember every math class you've ever taken? Yeah, I remember. 50 people said that. Okay, 40 of these students happen to be in Math 1108. And of the Math 1108 people, when you poll them, 20 of them remember all the math they've ever done. Now the question is, how many students who don't remember all the math they've ever done are not Math 1108 students? And how many Math 1108 students don't remember all the math they've ever done? Okay, so what I would do here is I would set up sets. So let me say M equals the set of Math 1108 students. R set of students who remember all the math they've ever done. 2, diagram. I'm going to go in here's my universe. It's the school that we're talking about. And there's the set M and the set R. Step 3, fill out diagram, which I would do on that picture. So what do we know here? We know that, let's put this in red, of the math 1108 students, 20 of them remember all the math they've ever done. I want you to realize that what this is telling you is the intersection of two sets. In other words, that just gave you information on the most overlapping region. That number comes in first. Fill in 20, most overlapping region. Okay, then what else do we know? I know that, yeah, so now I know that 40, let's put this maybe in green, 40 students are in the math 1108 circle, right? Now, if you had originally come and put 40 like here, for example, you would be wrong, right? Because it's not 40 right there. In fact, with basic arithmetic, if I know there are 40 things in the M circle, then outside here, there must be 40 minus 20 things equal 20 things over here. So for the M, take 40 minus intersection. So now in the M circle, there are 40 things, and I know that there are 20 in the overlap and there are 20 outside the overlap. What else do I know? I know 50 students remember all, I know that 50 students remember all the math they've ever done, which means in the R circle, there should be 50 people. So this is 50 minus the 20 that I already accounted for over there. And so that's going to be 30 people. Maybe I should put this 20 to say that I'm subtracting the red 20. So there are 30 people over there. For R, take 50 minus intersection. Now, what is the sum in all the circles? Note sum of circles. There's the 20 plus the 20 plus the 30, which means that is 70, which means there are 30 outside the circle, because it means that there is 100 minus 70 equals 30 outside. So there is 30 people out here. So this leads you to a diagram that looks like this. And you don't have to draw the diagram twice. I just want to clean up the markup a little bit. There's 30, there's 30, there's 30, there's 20, there's 30, and there's 20. And now I can answer the questions. How many of the students don't remember are not Math 1108 students? So A, I want all the people that are outside the R circle, and at the same time, they are outside the Math 1108 circle. This is 30, because I can just look at the diagram now. I've done all the arithmetic. How many Math 1108 students don't remember? So I want all the people in the M circle that are not in the remember circle. And that's the 20, the green 20. So this is outside both M and R circles. This one says outside our circle, but inside M circle. So basically how it's described, when they describe to something to you, you're going to basically says, is this inside this set or outside this set? That's what you want to figure out. And with the arithmetic that you do after you fill out the Venn diagram, you can actually answer the questions very easily. The hardest part here, and this is here, this will be step 4, arithmetic. The hardest part is actually getting to the picture. Once you get to the picture, you should be able to answer all the questions very quickly after that. So what I'll do is I will leave these in here for you guys to try because we're out of time now. So we'll knock these out very quickly next time. I would like you to try them before next time, but we'll wrap up right there. I think that's a good place to stop. No choice because I have the other class right now. So we'll stop right there. Thank you for your time and attention. I will allow you guys your leave. And yeah, I'll see you guys in the next one. Ciao.